right, thank you very much for sticking around and for this awards ceremony here. We had 20 plus posters that were reviewed and ranked, and I know the judges had a very complicated time in scoring them, so we're going to announce the winners. We had 2 honorable mentions, plus third through first, so we're going to call you up stage. We're going to take some pictures. If you'll stay on stage, we'll have a total picture, and then we'll go from there. So our second honorable mention was poster number 19, Viscosity of Plastic Modified Asphalt Binder, Charity Durr. Come on up, please. Forgot to mention Dr. Zaman raised some private donations for the awards here. I'm pretty sure he was shaking people upside down to get the money, but thank you, Dr. Zaman. Our first honorable mention was poster number 4, the prediction of unconfined compressive strength in Oklahoma clays using linear regressions. Matthias Lorraine, come on up. And our third place winner was poster 18, Long-Term Performance and Benefits in Combined BMD Chemical, Ajin Mashfi. And our second place, poster 15, Modeling Pavement Quality Index with Pavement Condition Data, Pundit Vakaldrayan. And our first place winner, Performance of Asphalt Mixes Containing Recycled Packs, is Sagar Goss. We're going to watch the videos of all 5 winners real quickly.
Hello everyone, my name is Charity Durr. I'm the Louisiana Tech undergraduate, and first off I wanted to say thank you. Second off, I'll go ahead and get started. We were testing the viscosity of plastic modified asphalt binder. We tested 3 different plastic types. We tested HDP, which is high density polyethylene, low density polyethylene, and polypropylene. So the reason why we did this is because these are plastics that are commonly used in plastic bottles and bags, and 3.04 million tons were landfilled in 2018. The good thing about it, though, is that if we do use these percentages in our binder, we can save a range from 630,000 tons to a range of 1.89 million tons from the landfills. So I'll go ahead and tell you how we did this. So we had our plastic types. This one is just what is commonly used. This is our viscometer. This is our temperature regulator, and what we did is we took the 3 different plastic percentages, 3, 6, and 9, 3 different temperatures, 135, 150, and 160, and 3 shear rates, 20, 50, and 100. We took 3 readings of each of the 2 samples for each of the plastic types. Over here we have the viscosity versus percent of plastic. As you can see, for all of these RPM, as plastic percent in the binder is increased, then the viscosity increases, which is what you would expect. Over here we have the viscosity versus shear rate, and these are based on temperatures. So for all of these temperatures, the lower percent plastic binder act as Newtonian fluid, so they weren't affected much by the shear rate. However, the 9% HDP and the 9% PP on all of these actually acted like shear thinning. Here we have our viscosity versus temperature graphs. Here is the AASHTO limit for 135 degrees Celsius, which is this line right here. We can see that all of these plastics actually were underneath the maximum limit, except the 9% HDPE, which means all of these are usable. This is based on the Asphalt Institute recommendations for the viscosity at certain temperatures for mixing and compaction. You can see that automatically the 3% PP works for all of these, but the others don't really fit into that category. However, this can easily be fixed by changing the procedure at which you're compacting or mixing. So again, the 3% PP works in all accounts. All of them were underneath the maximum AASHTO regulations, and they're all usable. So that's it. Thank you so much for your time.
Hi, my name is Matias Mendez, and I'm a graduate student at the University of Oklahoma. Today, I will present the prediction of unconfined compressive strength in Oklahoma clays by using linear regressions and random forest models.
Currently, most geotechnical engineers use standard penetration test data to investigate soil and field conditions. The SPT test is used in all the world. It is inexpensive, simple, and fast, and it gives a good approach of soil parameters. Geotech engineers rely mostly on SPT to estimate burying capacity of soil for designing structural foundations. The SPT test is also used to estimate UCS strength of soils. Currently, many states and private agencies are using this in situ test in geotechnical explorations for estimating its design parameters. 108 samples were collected and tested in the state of Oklahoma. SPT, UCAs, outer limits, moisture, and fine content were collected. The existing correlations or models for estimating burying capacity and UCAs of soils used by designers have some weaknesses, and there is need to develop better correlations or models. The use of artificial intelligence-based methods is gaining popularity due to its efficiency to predict models in all topics, from selecting a song and a movie in a multimedia platform to face detection, text editing, and social media. The techniques that enable computers that mimic human intelligence using logic, if rules, decision trees, and machine learning are called artificial intelligence. So what's the point of this study? It is to use SPT data and predict it to UCS by using machine learning, in this case, random forest models. The random forest model is a method that operates by constructing multiple decisions during the training phase. The final decision is up to the most of the chosen trees. The following tree is the proposed tree decision for UCS based on SPT, moisture, and fine content. Root mean square error, R-square, and mean absolute error were assessed for every possible combination of the studied parameters. Moisture, fine content, and SPT show the best result as a possible combination. The output of the random forest models and linear regressions for training and validation are shown. Random forest models show to have better predictions compared to linear regressions. The following linear regression equation was proposed. The authors of this study are thankful to OCAST, EST, the University of Oklahoma, and SPTC.
Hello everybody, my name is Aysan Ranjbar. I am a PhD student at Oklahoma State University, and today I'm going to present our work on long-term performance and benefits of combined balanced mix design and chemical warm mix asphalt technology. I would like to acknowledge Ratul Mundal, my co-author Ratul Mundal, and we are working in Dr. Mishra's research group, and our collaborator for this research is Dr. Fuji Zhao. The concept of warm mix asphalt is evolved with the fact that when asphalt is exposes to very high temperature, it gets oxidized and becomes very stiff. And if we reduce the asphalt production temperature, then we can improve the cracking performance. There are several types of warm mix asphalt technology, which is foam-based and organic additive-based and chemical additive-based warm mix asphalt. And so when I speak about warm mix, the temperature range is 220 and through to 75 degrees of Fahrenheit. There are several benefits of warm mix asphalt. It is the reduction of emission, the energy usage, and the fumes produced in field. The technology of warm mix asphalt is relatively new. It started in 2005 in United States, and the implementation increases over the years. And this table shows the percentage usage of warm mix in Oklahoma, and it shows that how it increases over the years to 58% in 2015. So our research is aimed how warm mix asphalt technology and combining it with balanced mix design can help significantly in the performance of warm mix asphalt. We have 4 different binder types with 2 different mixture types, and we have 3 different aggregate types. And also in this research we focus on chemical additives. The literature shows that how reducing the temperature can improve mass loss, and also the cracking potential using DSR stiffness parameter or Glover rule parameter. Also, we are going to use mechanistic empirical pavement design to study performance of warm mix asphalt and balanced mix design and compare them. And also we are going to do a life cycle cost analysis. Further, for my PhD thesis, I'm going to use numerical modeling and like discrete element method to model the stiffness changes and changes of binder, and also the behavior of cracking of asphalt. And finally, I would like to acknowledge Ingevity and ODOT for their collaboration.
My name is Pandit Vorkatulin, and I'm a student at OSSM. Today we're going to be talking about modeling pavement quality index with pavement condition data. Now, governments have a pretty limited budget to spend on maintenance and repair of their roads. They have to have some way of prioritizing one road over the next. In Oklahoma, that is the Pavement Quality Index, or PQI. The PQI is made up of several other indices, and in Oklahoma, we collect those once every 2 years. I mean, collecting this data is pretty costly and time-consuming. So we wanted to find out whether we could include a simpler way to quickly evaluate the condition of roadways. We used ODOT's pavement database, which is the database they use to evaluate PQI. Accordingly, it includes a plethora of different attributes about Oklahoma's roads. To prepare this data, we had to eliminate some of the segments that had incorrect, missing, or just blatantly false data. Next, we applied a simple linear regression to the data. We found that to be accurate, we had to group the data by pavement type. We also found that ride index had the highest R-squared value, which means it had the highest correlation to PQI, which isn't surprising. PQI is heavily influenced by ride index. After that, we separated 70% of the data to be used in training a neural network. 30% of that data would be used to test the neural network. And even though we had a pretty accurate linear regression model, we wanted to see if we could find a way to more accurately predict the data, and we did. We found that approximately 70% of the time, that neural network was able to get within 5% of the actual PQI value. And this is pretty exciting. We've shown that we can make a model that's pretty accurate. In addition, this model can be used as a base for a low-cost device, especially because this model inputs ride index. And ride index is basically just how bumpy a road is from the perspective of the driver, which means that it can be incredibly easy to calculate, especially compared to other attributes. In conclusion, we've been able to develop a model that, even though it's not accurate enough for official use, it's acceptable for quick informal reference. Given distinguishment between different pavement types, we're able to model pavement quality index from ride index. Now, I wanted to thank OSSM and Dr. Rahman for giving me this opportunity, and thanks for listening.
Hi, my name is Sagar Ghosh and I am a PhD student of Civil Engineering at the University of Oklahoma. Today, I am going to discuss some of my research findings, use of post-consumer recycled plastics in asphalt mixes. 37.5 million tons of waste plastics were generated in the US in 2018. Use of waste plastics in asphalt mix can improve the performance. However, the use of post-consumer recycled plastics poses several challenges, including mixing process, mix volumetric, and performances. Also, additional problem can be arised if a balanced mix design or BMD criteria is considered. The specific objectives of this study are to identify a suitable mixing protocol for dry process, to study volumetric properties, to study performance using the balanced mix design criteria. At first, an asphalt mix having a nominal maximum aggregate size of 9.5 mm and PG64-22 binder was designed using the BMD approach. 3 different percentages and 2 different types of post-consumer recycled plastics, namely low-density polyethylene and linear low-density polyethylene, were incorporated in the mix using the dry process. Volumetric properties were determined for both control and modified mixes. Also, indirect tensile strength test, ideal asphalt cracking test, and hampered wheel tracking test were performed to assess the performance of these mixes. The first challenge that is encountered in this research is the mixing process, and we will discuss it next. 3 approaches for plastic mixing were investigated. Of these 3 options, approach 3 was finally selected. Room temperature plastics and heated asphalt binder were added to the preheated aggregate simultaneously during mixing. The problem with the formation of paper-like films and sticking with the pan were eliminated. For the volumetric properties, both GMM and GMB was found to decrease with an increase in the plastic content. This is primarily caused by the low specific gravity of plastics as compared to the aggregate. Also, the reduction in GMM was higher than the reduction in GMB, which results in increase in densities. Let us look at the performances. Plastic addition increased rotting resistance but decreased cracking resistance. Stiffness contributed by the plastic particles is responsible for this phenomena. Also, plastic addition decreased moisture resistance. Based on ordered BMD specifications, 0.25% LDP, 0.25% LLDP, and 0.5% LLDP satisfied BMD criteria. So key findings are: approach 3 selected for mixing protocol. Plastic addition increased densities and rotting resistance, however decreased cracking and moisture resistance. 0.25% LDP, 0.25% and 0.5% LLDP satisfied BMD criteria.
Thank you all for watching my video.